In this session, we'll look at test number 2 and test number 3 and why they matter. Test number 2 is between active and independent Earth. This is a polarity test to confirm that the assumed active is, in fact, the real active line. The voltage here should be the nominal supply voltage, in this case 230 volts. Test number 3 is between active and consumer neutral link. This test is less obvious but important. It measures the voltage between the active and the consumer's neutral link. The voltage should match test number 2 at 230 volts. Why should these voltages match? The path in test number 2 goes ground through earth resistance, 25 ohms, while test number 3 connects to ground through the MEN, multiple earth neutral, link, and then through similar earth resistance of 25 ohms. Because the MEN link effectively shorts the neutral link to earth, both measurements should show the same voltage. A common issue is missing MEN link. Sometimes, an electrician might forget to connect the MEN link during the installation testing phase, which is often the last step. To simulate a missing link, we change the link resistance from 0.1 ohms to 10 mega ohms open circuit. Test number 2 remains at 230 volts, but test number 3 drops to 86 volts, clearly showing the MEN link is missing. What is the acceptable voltage differences? If the MEN link is connected incorrectly, such as to be insulation instead of the copper, this introduces high resistance, 300 kilo ohms, and still causes a noticeable voltage difference between test number 2 and test number 3, around 15 volts. Even a small resistance, 20 kilo ohms, can cause a 1 volt difference, which is why these two voltages should ideally be identical. Ensuring both voltages match exactly is crucial for verifying that the MEN link is connected properly. A common question is, what if the earthing resistance values for test number 2 and test number 3 are different? Let's take a closer look. Suppose we change the independent earth resistance to 500 ohms. The voltage still shows 230 volts and remains unaffected by this change. This is because we are using a high impedance digital voltmeter, typically with an internal resistance of 10 mega ohms. The difference in earth resistance becomes insignificant, as 500 ohms divided by 10 million ohms results in only about 0.05% error.